Okay, good afternoon, all of you. So we'll start this session. I think last class I have given the exercise. Okay, I hope some effort you must have taken, but I'll be giving some details now how to do this exercise, which is problem 1 in exercise 1. And this is the problem which you can read, and there's another problem. One of them is differentiating the function to describe the motions, velocity and acceleration. And the other one is integrating the function and getting the displacement and the velocity. So here it is acceleration is given, here it is the displacement. Okay, so we'll spend some time, then have a little more details on that, and we try to work it out whatever the results they are asked for. Any effort has been taken by people already? Any attempt? Anybody? Anybody has results now? Okay, let's start work it out on this. So what is given is the displacement, which is a function of time, okay, which is varying t cube minus 6t square plus 4. And by doing this exercise, we will learn something on the defining the functions also in Mathematica, and we will understand little on the derivative part and integration also. And later stage, you will learn the integration, numerical integration and numerical differentiation. Okay, and how to give the Mathematica input, how to make a plots, and how to get the information on the plots. All these things can be seen now. Okay, we will start from the displacement as a function of time, which is defined with a semicolon and equal. Okay, we'll assume for the time being we are defining like this. Later on, we will try to clarify what is the meaning of equal, semicolon equal, okay, and double equal. So these are the things Mathematica commonly used. For example, we will be using things like equal will be there, double equal also we will use, and we use semicolon. This is also being used. Everyone has certain purposes, and we will see one by one when you use. So when I define like this, it is delayed equal, and it can be called, which means delay means whenever it is called, this will be evaluated. So this is also, for example, displacement for a given t, whenever I call the d of t, it will be evaluated. So whenever this semicolon equal, when you should use this variable t underscore. Okay, and when you say t with this t variable can be any variable in later stage. Okay, I can have a d of x. If I use it, that's same expression I can get it. Okay, so we will start from this and learn this process, and we'll come back some more details on the Mathematica way of handling things also. So now this is the function which is given as t cube minus t square plus 4. Okay, so now we know how to find the slope of a
Sir,
given.
a small doubt. In Fortran and C, we use functions, subroutines.
Yeah.
How does it is different from delayed definition and ordinary definition? D of t and dt underscore.
D
There.
of t and no, we cannot, when you define this with the d of t, when you define it, it will be two possibilities are. One is equal can be there. And I'll take this itself. What is the advantage of? Let me go back. Let me come back to you start from here. So this is the function which we will define now. Okay. So now I wanted to find out d of say 2.0. I wanted to find out this. What is it? Which means substitute all the values of t and get it now. Okay, minus 12 is the answer. Now, the d of t, what we has been defined here, when I called that is evaluating. Okay, so now let me take d of, instead of a variable t, I will put it as x. I'm getting the same equation what has been given here in the variable x. So this option is available for you. For that matter, you can have any variable in this place, you will get the same equation again and again. Okay, So this is one of the major advantage that you have, that when I define like this t can be any variable. Instead of t, I can have y, r, a, b, c, any variable that can be used. The same function you'll get back. That's number one. I think you get the point now. I'll put an S. I'm getting the same thing again. So variables here, whatever I'm going to change here, it need not be t. It can be something else. The same function I may be using for two different purposes. Then I can use one time at one variable and another time on some other variable also. That's faster. Okay, so now this is the first part of it. Second part is delay things. For example, same, let me write d of t underscore equal to, I'm not putting the semicolon, but I'm just adding this. You can see here. When I enter this, you see what you get. I don't have an output. Correct? The semicolon equal, I'm not calling the function, but it is being defined and it is available for you to use any moment. But here, at that moment, it is equal to declared there. Okay? Therefore, it is coming instantaneously. At that output itself, it will be appearing. Here also, you have an advantage of varying the variable. For example, d of y, I make it here. Okay? I'll get the, at that moment, I'll be getting this. This is redefined here. Whereas when I use this one, when I enter this, I don't get the output immediately. Whenever I call the function with a particular variable or particular number, that will be coming to you for you to use. Okay, you can see the difference between this and this. This is instantaneous. Just give. It is assigned equal. Whereas it is delayed assigned, which means I can call it at any moment and get the value of the number for a given value of the number. For example, d of t, if I enter it, I'm not getting it. Whereas here it is being given. Then I'll give a range of values for it. For each value of that, it will be calculated. For example, I can have a list. One more parameter I can add. And this is the list which can be created for the different values like 1. I have a 3 and 4. This is the list which can be created. Or you can make a table of this. I can have a table. Table of. Now, when I add this, just open it. This is a list which are going to make it in the form of a table. This contains the table which are going to generate. What is the generation which you are going to make? T, comma, T of T. Okay. Now the T can be vary from 0 to, say, let's take 5 in steps of 0.1. Okay. Now there is a small error here. I just missed the variable here. Okay. That has been added. Now you can see that's being tabulated here. Okay. This numbers I'm able to get it just by I'm creating a list here by using this. This list can be used for plotting it also. So or this can be add here itself, plot list to plot here itself, which means it is equivalent to data is already being created. If I add a list plot here, it doesn't matter for me. I don't have to really make another statement, but I'll include here as a list to plot. What are the parameters which is required? You will enter here, and this is being listed and plotted. Okay. So which means list instead of need not be a list directly as a numbers all the time. I'm having already a table. The table already we has the form of the list of the data that's being plotted here. So the difference between delayed, this semicolon equal is delayed, it is being called every time and that will be evaluated, it's available. Whereas here it is when it is equal, but the purpose of both seems to be same. This can be used any way you like it, but only thing is it will be evaluated immediately and assign this value. Whereas here, whenever you call it, it assign, and next value it will take automatically. Okay, so that's how it is being used. If you practice it with the different problems with the different forms, then you will understand it. For the time being, you can accept that this will be delayed equal. This is equal. Double equal is the equal, equating them. Okay. That's what the meaning of the double equal, what we have been given here. So equal is assigned. Okay, double equal is, I'm sorry, equal is instantaneously you are assigned that value. Double equal is you are equating them. Semicolon equal is the delayed equal. Okay, this is the delayed equal here. Now this is the delayed equal here. We have defined the displacement and we have taken the velocity, and velocity you can see it is being generated numerically. And how do you do that numerical thing? Initial value derivative into the delta t. This is the derivative of that, and take a delta t. For different delta t's and corresponding d prime of t0, you will get the velocity component of this numerical. These are the points which we have taken d prime of t0 for various points. And you have an acceleration here, which we define it as ACTT, or you can directly also take as a double prime of this one. Okay, this is double derivative, this is single derivative, this is double derivative. That's what it means. So now you can take d of t. Look at the first derivative of here. This is the first derivative of the function. You can see here. You can cross check it whether the derivative is correct or not. Minus 12t plus 3t square is the first derivative. Second derivative is a minus 12 plus 6t. So it's by look of it, you can get an idea. This is going to be a t cube equation, acceleration, displacement. And the velocity goes with the quadratic like t and t square is there. D double prime is almost like a straight line acceleration. This is what the features that we could able to see by looking at this equation as it is. Is that right? Are you able to see that? It's a t cube equation. Okay, t square plus 4. Here, when I take a first derivative, I find the quadratic form. The velocity is in a quadratic form. D double prime is acceleration, which is a you can see this y equal to mx plus c form. Okay, that is the form which we have. Now we will plot all the three of them. Okay, we wanted to change the time and look at the plots at a time. All of them at a time, because one variable t0 or a t is the only variable which connects all of them, right? In which now you can see the advantage of what I mentioned here. Now this delayed equal, what one place we have used as a t, other place as a t0. I think you will appreciate now what is the purpose of having accepting this with a different variables. Various possibilities are there to change this t underscore can be any variable. Here it is, you can see clearly I made it as a t0. T0 is varying here, whereas here it is t. Okay, now I think you will appreciate why this is kind of variations in the variable should be accommodated when defining the function. Same function in its derivative when I take, variable is same, but what I change it to t0, where I am plotting t0 as a variable in the list form. This is the list, t0 and d prime of the t0 and t0 d of t0. Okay. Here the same variable t as a function of time 0 to 5, whereas same function t0 in the form of a list I am generating starting from t0 to d of t0. So you will understand now that's a purpose. Okay, now I have given some of the details here. Let's first come to the plot. The first plot what we are making is the d of t, which is the displacement as a function of time, which is a t cube, which means with respect to the t variation, it very much faster, is it not? The t cube is going to be much faster. And of course, this is coming down and goes up. So now we can see by adding this something like tooltip d of t displacement within the square bracket, which means if I place the cursor on these curves, you can see this is the velocity, this is the displacement. This straight line is the acceleration, and this is the slope line at this point, tangent line. Okay, so now you can see these are the options which is available. This, if you practice it now itself, you will always try to have a clear-cut picture about what you are trying to plot. Tooltip provides this information on the screen. Then we are plotting with this tooltip d of t, where t is varying from 0 to 5. Next is tooltip v of t comma t0, where t0 is varying here outer. T is varying here. Okay, this is the tangent line. At every point of this curve, blue curve, I am locating what is the tangent, and corresponding magnitude has been evaluated. That magnitude is going to be this curve. You can see here. Okay, on the blue line there is a tangent. That is at each point on the blue line I am moving it, which corresponds to the magnitude. That this is the magnitude of this slope of this blue line. Okay, when it comes here, okay, the slope equal to 0, that is crossing here. That can be seen. That's the velocity curve. This is the displacement curve. Whereas this acceleration goes linearly. Okay, so maybe when I bring it to the 0 position, you will understand the tangent. You can see the tangent is parallel to this. Tangent is parallel to this x-axis. At that point, you can see this goes to 0. So which means I am trying to locate every point on this displacement curve, then find out the magnitude of that slope, that is the green line on which this blue dot is moving. Okay, and when slope equal to 0, which is going to parallel to the x-axis, and any other point, you can see that's coming down and it changes. This is how the behavior is coming. So visually, I am able to see what is the meaning of a tangent or a derivative of a displacement, this line. Okay, if I take a derivative of this, I plot it, this is what I will be getting it. That is being found at every point. Find out what is the slope and the magnitude, and may plot that magnitude. Now it is negative and it's going to shift the 0 axis and then moving up. Okay, this is what the relation connecting to this. In fact, you can try from acceleration to velocity to acceleration. If I take the slope of this and make a plot, I will get this straight line. These dots, if I allow to move on this, then I find that this will be moving. When it is moving at every point, then they are getting a slope. That magnitude is going to be this straight line. So every f of x, there is an f prime of x that can be generated like this. So here we have taken a specific case where you have the displacement, corresponding velocity, and acceleration. So now all the three of them, in fact, 1, 2, 3. How many graphs you have now? 1, 2, 3, 4, 5 of them are here. 5 are, yeah, 3 graphs plus 2. 2 dots and the slope also. 2 dots and the slope, which means 1, 2, 3. There is a fourth one is this tangent, and then there are 2 dots. All of them has been put together here. So first part is the displacement tooltip. Second one is the tooltip is the tangent line that has been done. Then third one is d prime velocity. Fourth one is the acceleration. Okay, that is being plotted. Okay, so this is what the results correspond to all of them. And the variables are, for this, all of them is t equal to 0 to 5. And other place I have a t0, which is varying for the creating a list plot for the function which is already being defined with the delayed equals. So you can see the fantastic advantages of this. And this can be comfortably can be generated, and one can look into it. So now the list plot, what you have getting it here is, you can look at the points that is there. Every point of it, for example, this is the point on the what is the point? On the blue line. This is the displacement. This is the blue dot. You can see there is a blue dot. Corresponding blue dot on the green is the magnitude of the derivative that is being taken here. That's already we have made it as a full curve, and you can see that is moving on that. Okay. This is what the tangent curve for this blue line. Okay, what is the next part of this problem? So I think we have plotted the velocity, acceleration. In addition to that, we have plotted the x also, displacement also along with that. Okay, now you can see that when the slope line equal to 0, which is equivalent to, this is the velocity whenever you find this slope equal to 0, which means the velocity curve should be crossing the or approaching or reaching the 0 point here. This is the velocity 0. Then it is going up. Okay, that's the curve which you are getting it. And you can locate this point. How do I locate it? We have a d prime already, which is available as a function here. You can see minus 12 t plus 3 t square is the d prime. I have equal to 0. Find out the value, okay, at which it goes to 0. So when t equal to 0 and t equal to 4, it goes to 0. Okay. Now corresponding to t equal to 4, if you find the displacement, this is what the point that you will be getting. So how do I find out that magnitude? It's very simple for me to simply substitute that on the d of t. Okay. Substitute t equal to 4. So this number, what we get is minus 28. You can see you are here to minus 28. Correct? The magnitude of displacement at which the velocity goes to 0 is minus 28. I'm able to look at that point. So now we have all the information that is required for the dynamics to describe when the displacement is behaving like a t cube minus 6t square plus 4. So what I expect, where will you have a problem is that this is, what does this mean? This is very simple. At initial point given t0, what is the magnitude of y-axis? Okay. Then derivative of the y-axis into the x-axis will give another point, no? So that will be added because we are taking a very close points, t2, t0, very close to line, the derivative which is taken. So this is like a y-axis value. See, this is something like a small rectangular structure which you are trying to generate and then try to get the value of the d. So this is the points. I have a d prime derivative I have taken at each t0. What is the derivative? And this is the acceleration, of course, that will be easy. So these two will be used for generating the point and the derivative. Okay, that is what this every point, find out what is where is the location of the point and the corresponding derivative. That is what these points are. That is being done, and every point of it being animated. For animating purpose, we are using the main plate and put all of them together. Show. Use the show. Okay. Manipulation is what? This is the points, which is also equivalent to 0 to 5, 0 to 5, but it's going in steps of 0.1. If you wanted to make closer and closer, then you just make it smaller value of instead of 0.1, you can make it as a 0.05, it will get doubled. No, 0 to 5, you can divide it by that, so you'll get something like number of points will be, how much will be there? 5 divided by, you can have a 5 divided by 0.05. How many points you'll have? This is option for you to change 100 points. If I make 0.1, how many points? I have 50 points. This blue dots are 50. Okay. If I animate it now, you can see it is going and coming back. Okay. I just wanted to retrace the path again. To do that, just pick the arrow again. The W arrow, you make it. Okay, if you wanted to slow down and see them, just this is slow air. You can see it's moving slowly. So now because the increment is 0.1, it's a 50-point movement. If I make 0.05, it's going to be 100-point movements. Okay, that's what the option that is available for you to see the. You can see it is incrementing by 0.1. Now I can change this to 0.05. Let's see what's happening. Keep it the window comfortably and then make a change and then bring this back and forth. If you slow down, you will see how much is this. This file will then change the parameter. So animations can be done and we can take the output. GF file can be created. We can do all sorts of things. The whole thing can be explained because when you create this with the tooltips, because you just put the cursor on that, you have the curves details. Okay. And we have given those details here. See, displacement is given, tangent line is given, velocity is given, acceleration is given. If you wanted to add a point also, that point can also be added. This is point on this blue curve, which is the displacement, and this is the corresponding magnitude of the slope at that point. Magnitude of this. What is the magnitude at this point is this point. That is what is tracing the velocity curve. Okay. So this is the simplest thing which you can. So try to understand this little more, but later on you will get a clear picture when you learn about the so-called integration and the differentiation numerically. Actually, the whole of the physical problem in the Newtonian mechanics will be differentiation and in an integration. If you know how to do this differential integration numerically and analytically, you can understand most of the things that are happening in the Newtonian mechanics. Okay. So that mathematical part, what is what, how to connect them, that you should pick it up. Once you have that, then it will be easier. So now we have done the differentiation and looked at the problem. Now we'll go to the integration part of it, next problem, and then try to see. So when I say remove global, okay, with the back, some dot is there, and then star with this. You keep remember this, and if you add this, if I enter, the whole thing will be disappeared. Whatever which you have done so far, that will be disappearing. It will not be available for the next session. So in this, I have a next session, next problem. Before that, what I do, first thing I will do is I'll erase the same thing, all the things, because similar function I'm defining it, but functions are different. For example, look at here. I'm integrating v of t is what has been defined here is available in the v of t in the form, but it is a different function. Okay. Similarly, I have a displacement and I can have acceleration also. Okay. This is the acceleration part. So they will be different. So they will get clash now. To avoid that, what you can do is you just add this statement for everywhere whenever you start a next session of it. Within the notebook, if you start this, you do it, or any fresh notebook when you are started working on this, you can do this. So now I'm going to enter. By entering it, okay, just see what is happening. This will be disappeared. Okay, because we made it remove all the required the variables whatever you had used. So you don't have to worry that. Now you are going to start the next session. What is the next session is a particle P moves along x-axis with acceleration A at a time t is given by, this is what your acceleration, meter second minus 2. So maybe you can add it as a second minus 2 with the exponent second minus 2. Initially P is at the point x equal to 4 meter, which means x0 is given. It is moving with the speed of minus 8 meters per second in the negative x direction. Find the velocity and displacement of a P at time t. Okay, the particle p moves along x-axis. This is important, which means whatever which you are learning in the Newtonian mechanics, there are many physical quantities or vector quantities. So the whatever which you have learned as a displacement, as a velocity, as an acceleration, they are all vector quantities. That's why the problem is described like, suppose the displacement of p from O at a time. This is what it means, a particular direction. It has a direction. Because it's the direction quantity, we are taking a derivatives, and that's also a directional quantity, and double derivative is also having a direction. That direction is fixed. Okay, in this case, this is a one-dimensional problem which we have taken. So therefore, it is important that you can remember that we need to have a axis should be fixed, which means reference axis which will be there, and our problem is handling the vector quantities with reference to this axis. This is an one-dimensional problem which we are handling right now, because problem clearly states P moves to O along the x direction. Some such things are added here. See, P from O, okay, is given by this is a time dependent, which means my x-axis is the time variable, y-axis is my displacement. In the evaluate, I'll get a y. Okay, or you can take t as a function of x itself. When I evaluate this, I'll get an x. X goes to the along the y-axis here in this case. T-axis, and the another axis is the corresponding displacement axis. That's what we are our graph is. There should not be any confusion on that. Okay, so now v of t we have to find out. How do I do that? Just integrate with respect to the dt and introduce a constant c1. Okay, if you want to introduce this and then evaluate it, substitute them, or directly it has been given already, that can be taken. But we want, when you integrate, we have to introduce a constant c1 that can be obtained by a proper initial conditions. Okay, right? That's what is given here. You can see here. I have a, after integration, I have a c1 plus 6t plus 3t square plus 4t cube. From this acceleration, I am getting a velocity which is being integrated with respect to time, because time is the variable here, and integration of this c1. Now, speed is minus 8 meters per second initially at time t equal to 0. So, which means I will take out this equation. I am taking this equation v of t here, here. Okay. Substitute at time t equal to 0 equal to minus 8, that is being given. Find out c1. Okay, if I find out c1 happens to be minus 8. That's what your initial velocity that has been found. It is reconfirmed by the process. Okay, so now we have taken here solution 1, and v of t is already available as a variable which can be taken any variable you like, but we have not used the delayed equal, because that's not necessary here now, because it's being evaluated and then it is assigned here, and I am taking that as a v of t. Substitute the SOL, which is C1 is not known, that has been substituted through SOL, because this is a rule form, it is available. I am just substituting that. V of t, I need C1, that has been C1 has been taken through the solution 1. It goes into this. And this V of t is redefined now. This is what with the initial or with the constant what you are supposed to need, that has been found and substituted. And this is the final value of V of t. Similarly, take the velocity term, integrate and introduce time constant. So what do we mean by that is, I am taking this V of t here, okay, it's already defined, V of t dt plus a constant C2. Okay, this has been found. And problem already says that at the point x is equal to 4m, okay, that's initial point is given. So I'll take this equation now, substitute that t equal to 0, find out C2, that's going to be C2 going to be 4. That's already there as a 4 meter, which is just been substituted back, and I'm getting the equation for the displacement, which is t power 4 t cube 3t square 4t minus 8t and 4. That's what the results for the displacement. I hope that this integration part is very simple. Anybody can perform, and you can do it by on paper and pen, and then try to work it out on this mathematical, so that we are sure that what has been done is right. Now we know the displacement, and we can just copy and paste that the previous thing what else we have done. We have V has been found for the slope, and VPT for the points which can be generated, and D prime can be taken, which is a derivative of that, and D double prime is going to be the derivative further, which means I have the acceleration, velocity, and displacement. You can see that velocity component is a p cube, this is t square, and this is t power 4. That's what the function that we have. I hope this integration part completely clear for all of you, and this definition of the function is also clear. Now this just copy and paste here whatever you have done earlier. There's a displacement, there's a tangent line, there's a velocity curve. Okay, the acceleration also is available, right? And other things are just adjust your scale what you want to have. Okay, as a plot style, plot range, minus 30 to 65, because that is the range which can visually see all the information. And then you have the points that what you need on the displacement and the velocity that is available. I think there is. We'll find out, and we'll make some corrections there. We'll correct it. No problem. So we will execute now. Okay, and in fact it has been separated from this. The first portion has been taken out completely. Problem 1. These options are available for you. Okay, by taking the proper formats. Okay, this we will learn little more now. After proper format, if you take, then I can separate one from the other. I don't have to have a. If I select this, the previous whole problem will be available, and if I select this, the whole problem will be available for you. And I don't have to evaluate the whole notebook, but I need to evaluate only these selected cells. Okay, these cells can be evaluated. Evaluate cells. I'm going to evaluate the cell. It's done already. And this is what the results that you have. So you can see that something is satisfied this. No, that's something problem here. As I have mentioned here, this should be one more time we will evaluate, because already the things have been defined. Given problem. One minute. What is the time range he is asking to plot? Huh? No, velocity and displacement. We have to plot that on. So let me try to have the range a little more, and then see what is happening to this curve. It is the same thing as the previous one. Okay. Start from the beginning. This is the first part of it. Second, third, fourth. It should work. There is some functions are available. That's right. So I think 3 is enough. We don't have to go for range. Up to 3 is enough. Where is it? It's here. 3 seconds. You have the so much of increase in the magnitude. So now you can see here, exactly similar to that. You have a line in which, so you see that 2 places I have shown the dot now, the previous one, but here dot is only on this. So what I did is, I have taken the dots only, both of them are derivative part, but I need to have one of them is the displacement, other one is the velocity. Now you can see the two dots can be seen. Okay. Now these dots will be moving. This is the tangent curve. And the one which is moving on the blue, or if you wanted to know what it is, this is the displacement. This is your velocity. This must be your acceleration. This is the tangent line, which I have defined everything consistently here. Therefore, I don't have issue at all. And this is what the line that you would get. And you can see that the slope somewhere goes to zero, somewhere about at this point. And that point can be located as what you have done in the previously. Find out that. Okay. So this is what the equation. Solve it and find out the real roots. It is t equal to 0.75721. At that point, it goes to 0. Probably that can be checked now. Somewhere about 0.75 is the x-axis going to be, the slope is going to parallel to this x-axis. You can see that's what this point. It goes to 0 and substitute that point into your equation, velocity equation or acceleration equation, whatever you like, and then check the magnitude of the velocity or acceleration. So you can see that this is about 17.42 is the acceleration. You can see that's the point. It's somewhere here. 17 point something is sitting here. Okay. Similarly, velocity also you can find out at that point. What do I do? Just take the velocity and then substitute this time. I can find out what is the velocity, which I know that's going to be 0. Because that's what we have used it to solve. Is it not? You can see here. This is what the velocity component that is being used here to find the slope. If I substitute that back into this, it will go to 0. Okay, that's for the time which you have. Okay, so this is the other part of it. So now you can see one of them is integral, other one is the differentiation. But information is what you try to extract is connecting the slope and the function and the slope, either integral or a differential. And you can jump from velocity to acceleration. So here you can see the previous case velocity is, do you remember what is the previous case? Velocity is what? Is it a curve like this? The previous problem. Velocity, and see, this is the velocity and acceleration curve. It is a straight line, whereas here, what is the acceleration here? This double prime. This is the square of that. And that's why you have a curved features are curved. For this case, this is the acceleration. This is a t square term, whereas in the previous case is a equation, straight line equation. That is what you have. Okay. So now, when you define same thing within the same notebooks like this, then if you find when you execute this will be get affected. When you execute this one, that will be get affected. See, now you can see this is being affected here. The same curves has not been retained. But if you want to get back this, then you have to execute this starting from again, evaluate the cell. Okay, now it has come. Whereas this would have been disturbed, it's gone. Okay, so therefore you should be a bit careful. If you want to avoid this problem, then what you have to do, change these variable names. You make this is as a D1, D1, V1, then acceleration 1 and VPT1. Then you come back to this, you make it as a D2, V2, acceleration 2, if you define like this, then this problem would not come. Okay, that's another way to take care of that. But it's not a problem when you are independently explain one by one. But when you wanted to put them together, then it's going to be a problem. So this is one way to avoid that. Other way is you can copy this and make it in another notebook and keep it as a separate problem. Okay. Otherwise, names should be redefined, which means you take it the first problem as V1, D1, V1, acceleration 1, then V2, D2, V2, and acceleration 2. Just name it differently, and then that will not be an issue at all. Okay. Is it clear for all of you? I hope this is the part of problem which you are. So now this can be done without even inclusion of this tooltip, the displacement, all this directly defined function can be taken, can be done, which I think I have already done it and I have shown to you also. Not a problem. The latest stage, when you learn more about these tooltips and other things, this time this can be done. And if you practice from the beginning, it's not a problem at all. Okay, shall we go to the next part of it? Any clarification you require now? Equal, delayed equal, double equals. So these are the things which you have learned, and you can always define the way you like the variables, the way you like. Okay. Any clarification? Can I go to the next? No response. Again, can I proceed to the next one?
Yes, sir.
Okay. I'll close this. I'll send you this again with this. Okay, better save it. Go to the next thing, which is again a simpler problem, which you all might have. Yes, we'll go to this free fall dynamics. This I'll close, save, close it. This is quite interesting now to see. Okay, so you're familiar with these things. I think all of them will have at least some exposure at school level and at higher level also. So gravitational acceleration, force, velocity, displacement, potential energy, kinetic energy, plots and animations, which can be done for any of these things which you like. So this is the linear motion, this is the rotational motion, one-to-one correspondence. So now, within the Newtonian mechanics, you have to remember four important things. Number one, the space, which is will be the vector space where you have a displacement, velocity, momentum can be there, and then derivative of that we have an acceleration also. It's equal to a force. Okay. Then you have the impulse, the scalar quantity, kinetic energy, then work and power. These are all the scalar quantities. These are all the vector quantities. So now we have the space with vectors. Then there is a time. So space and time. The space can be, as I said, it can be vector space, it can be velocity space, this displacement space, velocity space, or acceleration space. Now we have the time. Let's say time is the connecting quantity here. So space time, in which we have an important quantity, what we call this acceleration or the force. Okay, force and acceleration means you have dv by dt. Force means including the mass component. So these four quantities, physical quantities, are very important, and you should know how they are being get connected to each other. Okay. For example, if you have an acceleration, what is that is to do with the mass of an object? Okay. So what happened? This acceleration and the mass, if you connect it, what does it mean? Heavier the mass, acceleration will be smaller. So it resists the motion. What mass is resist the motion. Acceleration is reduces or a small for a smaller or bigger objects and higher for the smaller objects. So which means there is a resistance for the motion that is being created by this mass. So this mass is the scalar quantity, which is a very important quantity. So space, time, and the mass acceleration, these are the very important quantities. Of course, once you have the space time, I have the displacement will be there, velocity will be there. See, this is the time derivative. Again, take a time derivative of that, I have an acceleration. So starting from the space, using the time, I get the velocity quantity, right? And I have a velocity, again I divide by the time. Okay, take a derivative with respect to this velocity time derivative, I get an acceleration. So once I know the acceleration, there are various possibilities for the accelerations. So once I know the acceleration, you multiply with the mass, I have a force. And in between, we can have one more quantity, which is P, which is equal to m into V, mass. See, we have a mass multiplying by an acceleration, mass multiplied by velocity also possible, which is a momentum. Derivative of this is going to be force. Okay, our acceleration into mass is going to be force. That's what your second one. Impulse, of course, how short time it is going to act, del t. Okay, then from that you have the other variables like work, energy, and the power. You come to the rotation, exactly similar thing is there. Okay, these rotational motions, we have a rotation means there is an angular velocity which is involved here. You can see this is your angular component of the velocity, and this is a vector quantity. Omega is a vector, and the derivative of this again is going to be an alpha. And you have an angular momentum corresponding to the momentum. There's an angular momentum which is equal to r cross p. This is a vector quantity. This is also vector. This is also vector. Then force equivalent is the torque. Take a derivative of the. See, now you can see they are all will be playing with the space time only. Okay, with the different vectors. Position vector. This is the vector which is angular velocity. And here you have alpha vector. This is a vector. And you have a momentum here. This is L, which is connecting the space with the P also. Then torque, which is a force, which is similar to here what you have, R cross F. Then you have angular impulse, which is similar to this. And here is the half v square here of I omega square. And the work is now tau dot d theta, power is omega dot tau. So therefore, these things one should remember it when you try to learn things systematically, whether you are going to describe linear motion or a rotational motion, and how they have come from, and what is the origin for it, how do we connect from one to the other, that all automatically connecting from, for example, here if a mass, then I will go to here, it's a moment of inertia. I have a V and I have a omega. So like that link also one can understand. Keep them in mind, and when you learn about the rotational motion, you will understand more about this. To start with, we spend most of the time to learn Mathematica and also plus the linear motions. The later stage will come to this. Okay, now let's put some time to learn about this cells. What you have at the end, you're able to see there is a cell here. This is a text cell, and this is the text cell. This is also a text cell. What is the? How do you differentiate from one cell to the other cell? For example, this bigger line and small line connecting this. Okay, there's a shape like this with the line which is smaller than this. This is the text. This is the text cell. Okay, and how do I obtain the text cell? You can do this. Go to this tile. This is the text. This is the right, just a text entering, and that text can be given under the subsection, section, chapter, subtitle, title. You can come from here to here, or you can go from here also. The corresponding key operation you can see here, Alt 7 is the text. If you remember that Alt 7, if you enter there, you will be only entering the text portion in the Mathematica. Right. Okay, now you have the text portion means I just enter the F7. For example, if I look at this cursor positions here, horizontal means I am in the ready to enter the Mathematica statements like this. I have a number multiplications. This is the output. This is an input. Okay. Now Alt F7. If I enter, this is a text, and nothing happens to it if you give a shift enter. Shift enter is the statement or operation to execute your input. Okay, so this is the text part of this text part can be Alt F7, it can be Alt F6, F5, F4, F3, F2, F1. Okay, various levels. It goes to various levels. So come back again to the F7. This is what your F7, which is a text part of it. The text part will go to as a subsection, subsection, and then section. Then you have the what are the other ones? You can't forget. Subsections and section, chapter, subtitle, title. That's how it goes on. This is the order in which it goes. Then you have something like a code which you have, and then input also there. So these are all when you just enter it and then try to practice them, you will understand them. But what is important is input and text part. That should be the starting point. And later stage, you can pick up all these things when you start doing a particular problem which you wanted to give all the information about the problem. Then you will be learning about the title, subtitle, heading, subheading, subheading, all these things that you can learn it. So now all of them will be distinguished by looking at the cell structure. You look at the various forms now. If I have this type, which means it is a text alone. Look at this one. Okay, I think I'll take this one. I just copied already. I remove this one. See, this is expanded here. This is the input now. Square root of 3, see, this is the list. Whatever you have that can be given in this. List as it is will not do anything. If you ask to do certain things, it will do. For example, within this script, I am asking to find out square root of 3. 3 square root which can be entered automatically by using a so-called palettes here. We have a basic assistance here. This square root here. If I click square root, I'll get a square root here. Or you can do this by using a key operation that also must be available when you put it over here. You can see keyboard entry, control 2. If I do that, control 2, I'll get a square root. For every one of them, correspondingly, they must be typing his. You can type that. That's also given. So keyboard entry also given. This is keyboard entry. Okay. So like this, it's possible to see them. If, for example, infinity, which I don't have to come here, escape, press INF, then then press escape again. See, for example, this is square root. Infinity, I want to type. What am I supposed to do? Typing can be done by escape, put INF, put again the escape, you'll get a infinity. So if you wanted to have a theta, escape, Q, theta, I'm getting it. If you want to have a phi, F, what do you have to do? Press this, F again, press this. Okay. I want to have a pi, press this, put P, pi. That's what your pi, what we will be using it. Then and I wanted to have a alpha, beta, gamma, all will be available. Alpha, same style you have to follow. Beta, I have gamma. So escape, put that. Suppose exponential. See, for example, exp is the exponential. Okay, exponential 1 e power 1 means I'll just take out this and then put it separate again. Then come back to that. Exponential 1 is this e. Okay, and I wanted to know what is this numerical value. Put n. Okay, exponential, and same exponential can also be obtained like what you have seen in the symbol form. That should be done by escape, double stroke of small e. See, I'm getting this. Again, ask for the number n. Okay, so like this, it is possible for you to get this through keyboards. You can really get this information also. They're all the same. And one more thing is also available in Mathematica for exponential. Just use the capital E and ask for the numerical value. So these are the 3 different ways you can handle the exponential. Okay, so I have exp of one number. This is an exponent. This is also exponent. This is also an exponent. In Mathematica, either you can use this. This is a double stroke. This is a function as it is. So that is how you'll be operating on this. So otherwise, you can go to this, take a help, go through them. But see for arc, sine, cos, cosine, cos h. This is one type of a thing in which whatever is needed that can be used. You can see here alpha, beta, gamma. This is the giving an expressions of various types, including matrix, integration, delta, differential, everything can be seen here. Then this is alpha, beta, gammas with a capital, okay, and small, all possibilities are there. This is the various symbols connected to this. And this is the arrow marks of all possibilities, and these are some of the typical symbols that are possible, that are available for you to use. In addition to these palettes, you have classroom assistance. Again, similar thing. Some more additional things are available here. Okay. Then the palettes. Writing assignments. This is for writing purpose. Okay. These are the palettes that can available that can be used, and then you have a special characters also. These are the special characters which are also seen. These are the symbols, letters, symbols. This is symbol. These are the various letters that are there. For example, you want to look for a Planck's constant. Where do you look at? Okay, you can look at Planck's constant somewhere. H. How do I get it? Maybe in the typing set can be there. No. Okay, I just wanted to try here. This is long back. How do I get this Planck constant now? No. Special symbols. Well, that must be somewhere. This. No. Not here. Maybe just check in the writing assignments. That's what I'm looking for. Alpha, beta. No. It's here. This is H class. So multiply with 2 pi, you'll get the H. And H itself, I do not know whether that's given or not. Otherwise, you can define it also, not a difficult thing. So like this, other parameters also available. So you can see the W E also available, pi, which is another form. So there are various possibilities that are there that can be explored for this special characters. Now, what you wanted to say from here, now we will go back to we remove this one. So this is the input cell now, okay, and the corresponding output cell. Now, if I put decimal point here, that magnitude with an approximation will be given. Okay, if I don't put it, I am limited with the about 5-6 decimals it will be given. If I want to have a further magnitude, you can put the numerical value and get the number of decimals that you want. Okay, what is interesting here now, the input will be not like these two parallel lines at the top. You can see there is a triangular structure. When you have this with a triangle structure, we call it as an input cell, and output cell you'll get another small line like what you have here. So if I have a triangle structure with a line, okay, so this is grouped here, input and an output, and output sometimes we don't want it, we put a semicolon. So these grouped input and output cells, this is the standard forms, where the input and output is the standard form, which means this is what the standard form. Now suppose if I make an input of this type, which we call it as a traditional form, like what we write in a textbook. You can see there is a input. What you have here is same, but in addition to that, there is a dash 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 lines. Okay, you can see here. So if you have that, it is a traditional form. Output traditional form also possibility there, but maybe you have to declare it, which I have not verified it. Probably that you may be getting it also. I think output is also in a traditional form. This pi is not a regular standard form. You can see that pi what you have is different from pi what you are getting as an output. Okay, this is an output of that. Okay, so these are grouped input output cells in a traditional form. That is what they result that. You can see that there is an arrow here. So you can always check that you have a triangle structure, and then if you have a dashed lines like this, vertical lines, then it's a traditional form. No such lines in a triangular form, it is a standard form. So, okay, these are some of the cell informations, and this can be grouped. Okay, and various text forms that are available, that also we have seen. So now we will practice them, and then one by one we can learn further. Okay, we'll go to the problem now, which is a simple problem. Suppose I am dropping a stone from a particular height. The force what is acting is the constant force, because G is the constant acceleration due to gravity. Now you just see what has been done. This what did I do now here? Integrate this gravitational constant with the time, so that I'll get a velocity. We have introduced a integration constant as an initial velocity. So because G into T is a velocity, therefore V0 must be an initial velocity. Now the force what you have here is m into d square x by dt square is equal to ma. In this case happens to be G, because we are dropping an object, okay, vertically from a particular height. So let's take that's about 50 meters or so. That's what your initial position of the particle, and initial velocity equal to 0. So now let's take from here we will come to displacement. Substitute this velocity here, integrate again, add that. I'm getting this. Is half gt square plus t v0 plus x0 is constant, which we introduced, initial position. So we have a force which is constant here. Okay. Now, given this force, how do I find out the velocity and the position or the displacement? By just performing the integration, which means my force is constant. For a given mass, there is a uniform, the constant force that is acting on the object. That is nothing but your gravitational constant in this case. So if I take 50 meters from height and release it, so it comes down due to the acceleration gravity. And the gravity, now this acceleration is a vector quantity, and it is pointing down, we are taking as a minus sign. Okay, and then x0 is this 50 and v0 is 0. Now I am defining this as a constants, because this will be used in your equations wherever I like. For example, dt with a constant, what is going to happen? We'll just see. First, we will execute this one by one, starting from here. Remove all, because already some 8 statements which were there, which we have done it, that has been taken. There's no symbol matching global, so which means this. We'll check what is this. There is some typing problem somewhere. Okay, we'll copy and paste after. So we will, time being, we'll accept that's not a problem now. V of t is this one. D is the one. This is the displacement. And my acceleration is g. This is the g is the value. That's what you are taking for integration purpose. Okay. So G is minus 9.1. Now, what I wanted to know is that when I substitute this, it's already been done. When the semicolon output will not be, semicolon means when there is a semicolon, you will not see the output. For example, this I'm able to see here, d of t. So I'll enter this constants now. This constant I'm substituting, instead of equating them, I'm making it as a constant. Wherever I require this, any one of them or all of them, just use a constant. We'll take these values. For example, d of t requires initial position, initial velocity, and g. I just substitute that because I put it in a rule form. When I say it's constant, you take it because it's defined like this. It will take those values. For example, it takes the x0 50, v0 is 0, and g equal to minus 9.1. With that, you will get this result. You are getting it now? If I put a semicolon, that output will not be shown. That's all. That's the only thing that's going to happen. Now, to plot this, I wanted to plot this d of t. D is a function of t. Okay, this is not delayed equal, but we are just equated now, and it is available whenever it's calling. So now d of t with a constant, this is the equation. It starts from 50 meter when t equal to 0, started coming down. And since it happens to be t square, it's sort of a parabolic structure. For example, if I make g equal to plus, you will see the parabolic structure, which you normally see. But here it is 50 now. You can see here the curve will be get shifted up, starting from here. Instead of coming from 50, it starts from 0 and goes going up. Okay. So now you can see that this is become a plus sign here, but we know this g is acting down now with the minus sign that should be taken, and it's starting from a height of 50 meters. Therefore, it will be coming down from t equal to 0. So this point where it is touching this t-axis. Okay, goes to, what is it? Goes displacement goes to 0 at that time somewhere here. As I said, the d of t, I can use any variables, t, x, y, z, or p, q, or whatever you like, you use it, and that's going to be same thing with the corresponding variables in each equation. Okay, which we have seen enough. We can plot it again with the d of r. I'm getting the same thing, but since this is already defined as a time and a displacement, that will be there. But only variables will be taken for plotting purpose or calculation purpose. So you would see the axis labels are retained, range also retained. Only thing the variable is, instead of t, I have just made it as a r. No issue at all. You can make it as an x, doesn't matter. Okay, so this is the issue that you should not get confused, that sometimes we use some other variable also when it is defined with this underscore distance. Okay, with an underscore there are two options, equal and semicolon equal. Right, next, velocity. Of course, we know that take a d of dt of t. They take a derivative with respect to the time. So this is represented like this, and I'll get a velocity curve. Correct? This is the velocity. Now I'm going to plot it. These constants are used here, which is already defined here. Okay. So these constants are substituted for the d of x. There's a requirement for it, or v of t. v0 is required, g is also required. Both has been taken. Or if you wanted to confirm that, what you can do, you can take v of t, just check here, v-o-n-s-t. Okay, 9.81 into t. Is it right now? Seems to be some problem. Yeah. Right. Okay, that's right. Okay, so now we have a plot that should be made, that has been made here for the velocity. So now for this curve is going to be a slope at every point. That is what this curve. This happens to be a straight line with a particular slope. What is a particular slope implies? It implies the passing through the origin, the negative sign showing that the velocity is pointing to the down. Okay, then for every minute of it, how much is the displacement? Going to be 9.81, 9.81, 9.81. It goes on like that. Okay, from 2 to 3, 1 to 2, 0 to 1. Find the slopes. That's going to be same. That's what the slope means. And you follow the same tricks which says what has been done earlier and try to check whether you can plot them in the form of the slope showing the points, and then try to confirm yourself that whatever I need, I'm able to get it here also for this. Okay. See, plot this. I have not added the tool tips, but I have distinguished by using the colors. So you can see here this velocity here, displacement is here, and this slope at T0. Also your tangents. So now you can see this is the curve. On the top you have the displacement and the evaluation of the slope at every point. That's going to be this straight line. Okay. So therefore this is what the results that you have for a free fall when there is a constant force, which is constant acceleration. Right? Here I have the tooltips. Okay, let's see. So I think this is clear for all of you. So this is starting from 50, it is coming down, reaches the ground here. This is the velocity curve. Starts from here and probably area under this curve will give the displacement, total displacement is possible. You can find out. Okay. Now look at the velocity displacement as a function of time and acceleration. So far we are fixed with the acceleration is fixed by this magnitude. Suppose acceleration changes. You can see here. You look at the curve, what you have here. I have a velocity and a displacement in which acceleration changes. This is one particular value of acceleration, 0.1. Now, if I accelerate, what happens to this curve? Look at this curve. See, you please remember that this is the velocity, this is the displacement. You can see this AT square. This is AT. Initial position and velocities are 0. I am changing the acceleration, the different acceleration if it happens. See, if you accelerate, you will cover the displacement will be much more when you are shorter interval of time you are able to cover the displacement maximum value. Velocity also going up, the slope is increasing, that we can able to feel it for a different acceleration. So is it fine? Is it clear for all of you? What is happening here? This is sort of an animation which shows that velocity and displacement for a different accelerations. Previously we fixed the acceleration. Here different acceleration that we are fixing it and then looking at it. For example, I stop here somewhere. At this acceleration, this is what the velocity curve, there's a finite slope, and this is what your displacement curve. I'll go to some other number. If I go to the exactly that 8.1, 9.81. That's correspond to the one of the acceleration which we have fixed it for acceleration due to gravity. 9 point, I think it goes in steps of 0.5, close to 9, 9.8. So to really move slowly, and this corresponds to the constant acceleration due to gravity. 9, or you can just enter here. That's all. 9.81 is this curve. This is the acceleration due to plots, acceleration due to gravity. Any other acceleration? Well, this is increasing further, it comes down. When you drive your vehicle, we do this one. We accelerate all the time. And the displacement will be more and more, which also implies that slope is increasing. That is what you will be observing. Okay, so this is what the meaning of your different acceleration corresponding to the displacement and velocity. Here it is a fixed value which we connected to the gravitational constant. Okay. I think we can stop here. We have a lot of other things to discuss afterwards. We'll show them. In the next class, I will be discussing more about this. So I think better you can ask a couple of questions and discussions. Right? Come on. I'll be happy to have some questions now to discuss about this simple issue of velocity and the acceleration and the displacement. Yes, please. Hello? Hello?
Yes, sir.
Sahin, you're around or somebody is around? So, any questions, any clarifications which you would like to have it on this? Yeah. So I'll send these programs now. You can practice them, whatever which has been explained today now. You can practice them. Then the other thing also you can have a look at it, because I have done some of this other curves. For example, I have a cos theta, sin theta. Okay, all these curves that we have here. You have the sine curve. The same slope techniques I have used here to show this. You see, sine and cos slope deviation. Go to the cos, take a differential, slope at every point. Then try to understand the next part is the tan, which is so typical. That also can be clearly seen. See how the slope is changing. The yellow ones are the slopes. Similarly, you can have a secant again. This is what the variational slope, and you can have a cosecant again, that can also be shown. Then you can have a one more will be there, cotangent. This is what your slope curves. And you'll get a clear-cut picture about what is really happening with respect to this derivative of these trigonometric functions. And here is the example of the derivative numerically. If I look at it, what is going to happen? Change the x by a small amount del x, substitute into the function, and the limit of del x goes to 0, I'll get this result of derivative. So sine, when I differentiate, I'll get a cos x. This is the numerically one can evaluate them. This is the expression in which change the limit of del x starting from 2 to 0.01. So now we can see they are well separated. Del x equal to del s equal to 2 now with respect to the substitution of here. If I make a plot, this is what we'll get it. So you can see the difference now. They are very much far, but structure has been reached already. And if I reduce the del x, the limit goes to 0, it goes and sits on the sine curve. This is what the meaning of derivative. You can select many such functions and then show that yes, this is true that del x, for example, instantaneous velocity take del t approaches to 0. You can define the instantaneous velocity. This is what the meaning of the derivative that is being done for other functions also. Okay, so again 3D plots showing the acceleration. V is a function of a and t, a and t, and these curves can also be generated with 3D plots. Look at it, and a is constant, and then look at as a function of t what happened to velocity. The other way is take the t for a given constant and look at the plots. What's happened, that can be seen. Similarly, here displacement. Here it is acceleration as a function of time and the different. This is at, velocity as a function of a and t. This is the displacement as a function of acceleration and t. These are three-dimensional plots. And individually, see, this is the beautiful animation that you have to look at what is happening with an object when you drop it from a meter of 50 meter height. This is what really happening. This is the distance covered at around this time. And this can be nicely generated by using a graphic objects. That's all, that's simple. And put it in a three-dimensional objects again. It can also be shown with the like a object, real object that is being dropped. Okay. And independent plots also can be made. Then you can look at them. Okay. Acceleration, velocity, and the displacement. And change the time now. Okay. And the velocity. This is the acceleration change. Slopes changes can be seen. And there are velocities, displacement. All are connected here. Show them all of them together at a time. And velocity. Now here another function. We have the velocity and the displacement. Plot is displacement against the velocity. This is what the nature of the curve. Then you make a potential energy, kinetic energy plots. And try to understand what is the dynamics which is going on. That is what you are interesting aspect of it. This is all been described in this. I'll send you this to the Shaheen. He may be sending to all of you and go through them. Okay. So, shall we stop here now?
Thank you, sir. I have a small comments to the
Please.
participants.
Okay,
yeah.
please.
Yeah, I'll be sharing this in the Moodle site. You can download it. The best thing I practice for learning is I just copy this in a new Mathematica file and shift enter. Then second thing, I change the parameters and manipulate it. That is how you can be an expert to learn. Yeah, you will be learning slowly. Yeah. You have any comments? All of you got the Mathematica software?
Yeah, that's important. Just clarify them.
Yeah, everyone, I gave your email address and other details to the company, and they told me that they have already sent all the participants the Mathematica software. That would be, they will be giving you for a period of 1 month, then they will extend it to another 1 month. Then after that, you can use even Mathematica Cloud. Whatever we are doing, that can all be done in Mathematica Cloud as well.
Yeah,
But
that's
the
right.
full software is with you right now, if you have. Thank you, sir.
Okay, thank you. We'll meet tomorrow's 2:30 class session.
Yeah.
Okay.
Okay, sir. Thank you once again, sir.